Hello. So yeah, my name is Maciej, or simply Mac. I would like to talk to you today about caches. So a small side note, why it matters. So I want to tell you what can you take from this presentation. So why caching matters? There is a couple of things. Oh, sorry, something happened strange. Okay. Okay, back. So usually when you think about caching, it's about scaling, about performance, about making things available to your services. Sometimes it might be about reducing the costs of your services, especially if we were thinking about the world of microservices. But caching matters pretty much in any application. So let's talk about why it matters. So the agenda for today is that we'll talk about the most simple form of caching, which is using a hash map. And then we will explore the reasons why it's not enough, so that you can build your understanding about what are caches, what are their strong sides, what they are leaking, and then you can understand how to pick a specific cache implementation for your particular case. Okay. So we will talk about those requirements. We will talk about popular solutions in the Java ecosystem and in the cloud ecosystem. And then I will do a small comparison of those caches and approaches to caching and best practices and worst practices as well. Okay, so let's talk about hash map. That's the foundation of caching, right? So a hash map is a simple data structure that allows you to put something under a specific key of some object in Java. You can use string as a key. That's a very popular choice, but it's not limited to string as a key. So you can use pretty much any class that implements proper hash code and equals functions or methods. And well, the hash map is very fast. You can easily access it in a constant time. You can write to it in a constant time, pretty much. But there is a problem. The first problem is that there is no automatic cleanup and there is no expiration policy. So what is worse, you can add things to your hash map cache, but you have no control over its size. I mean, you need to implement it. You need to check what is the size if you want to put something and you don't want your hash map cache to grow. So it pretty much very quickly happens to be not enough to implement caching properly. So one thing is no size control. The other problem is no eviction. So it means that it won't the hash map itself won't remove outdated data, right? It's up to you as a programmer when you're using a hash map to actually remove stale data from the structure. And there's no time to live, so you cannot say that, okay, I want this data to be valid for like next 3 minutes or 6 hours. No, you need to implement it by yourself, all by yourself. And the worst thing about hash map, in my opinion, is that there is no observability on it. So you don't know how it performs, if it works as a caching solution or not. You need to implement this all by yourself. Okay, so to sum it up, you can use a hash map because it keeps the data, and that's pretty much it. And it allows you to access it very quickly, but that's it. It doesn't give you anything more. And what you really need from a proper cache is time to live and eviction from cache. So when we're talking about local caches, about caches that are in the same process as your main application, you want to have some kind of removal policy so that you don't keep the data that is outdated or the data that is stale. So there's a couple of ways of evicting items from the cache. Least recently used, that's one of the policies available. The other one is least frequently used, which means one is, well, when it comes to removing data from the cache. LRU, sorry, least recently used, means that remove the entries that weren't used recently, because they don't matter right now. If they're going to be needed, then let's load them when they are needed into the cache. Least frequently, that was the least frequently used. Last recently used is another option. Okay, so we used some data, so they don't matter anymore because there will be some more processing and the new data will be required to be close to your processing. So that's last recently used. And then there is also an eviction policy based on size. If the cache grows too much, just prune the cache so that it doesn't occupy too much memory. Okay. Then the other thing that we want from a proper cache is monitoring. I've mentioned that before. So I want to know how often, when I ask a cache for a specific entry, how often it actually contains this data already there. And how often it doesn't. So that's the miss rate. Okay. So one example of pretty much most popular in Java world is caffeine. That's a local cache, very high performance. It actually can be faster than HashMap in a typical use. It supports async loading, which means basically telling the cache, okay, so use this code to load the data in the background without the actual client of the cache asking for it. So it can be set up, configured as a loading cache. And it works perfect when you have a single node of your application. You want to have some cache in your process. The other one that was quite popular is EHCache. That's a very mature library. It has an integration with Hibernate, so you can use it when pretty much out of the box with Hibernate. It can also act as a distributed cache. We're going to talk about these distributed caches in a moment. And it has very rich monitoring and management API. One that also is worth mentioning because you can work with it in mature code bases is YAVA25 from Google YAVA. I would say it's stable, it's well known. I don't think it's maintained anymore, but it's still used in legacy projects. Okay, so right now we're talking about single node application. You have like one node, you have your application working on this one node, running on this one node. But usually you deploy your applications into clusters, especially if you're in a microservices world. One node is just not enough. You want to scale your application. So you might think about, well, I might need a distributed cache. So I have a cluster, and then I want a cache that is going to work with all the nodes in that cluster. So that's where we need a distributed caching solution. And we want to have some shared cache state between those nodes. And there is a couple of problems related to that. One is that you need to be able to invalidate the cache between different JVMs. But it also gives you the ability to scale out, scale beyond single server memory, and provide things like high availability and failover, right? Even if one instance of your caching solution goes down, you have other nodes that provide caching to your main application. And again, one very popular solution that is worth mentioning is Redis. This is an in-memory data store. It's extremely fast. It has rich data types, so you can actually store objects into it, not just strings. And you can actually add some persistence to it, like append-only file log. Yeah, you can build clusters out of it and provide high availability caching, distributed caching solution for your application. The other one that is worth mentioning is memcached. That's a lightweight distributed cache. It's very simple in its model because it allows you to store key value strings only. But this provides a very high, well, it helps memcached to provide very high performance. So a typical use case would be that when you want to store something in that kind of cache, you come up with a string key for it, you serialize your object to probably JSON, and then you store this JSON. And then when you load elements from the cache, then you deserialize the JSON. Okay. It doesn't have any persistence, so it's not like Redis that you can store actually the data to the disk, but it has a lower overhead than Redis. And one specific that I want to mention here today as well is Apache Geode. Someone heard about it? Not many people. It's a very specific solution. It's actually, I would say it's more like an in-memory database that provides you with querying capabilities, transformations, and stuff like that. But you can use it as a cache as well, as a distributed cache. The thing is, it's written in Java. So if you have a particular desire to run everything on JVM, then you can use Apache Geode for that as well. And it has consistency guarantees like ACID-like transactions. It has integration with Apache Spark. You can do data partitioning, all kinds of different things. I would say it's more like a very peculiar solution for it to be used as a caching solution, but still, I think it counts. So, small comparison. Redis allows you to store rich data types. It has persistence. It has high availability support. Generally good general purpose distributed caching solution. Memcached, very simple, very lightweight. It's quite fast. And if you want to scale out your caching, that could be a good choice. And Apache Geode, enterprise grade, queries, transactions, pretty much an in-memory database more than just a caching solution. Okay, so we've been talking about two different kinds of caching solutions so far. One is local caching and the other one is distributed caching. So when to use which? If you really need very fast cache, then you probably want to use local caching, for example, Caffeine. And that's very fast response times, but then it's just one single process that it is available to, and it's memory bound by the available memory for your node. And we're going to get back to this in a moment. If you have a requirement that you need to share your cache across different JVMs, if you want to scale it horizontally, then you might want to think about distributed caching, but then you need to take into account that it's going to introduce latency. The network latency will add something like 5 to 10 milliseconds just for the network call. Okay, so when to choose which? Simple summary. Let's talk about more requirements. We want our caches to be consistent. If we have a distributed cache, we want to be consistent between the different nodes of the caching solution, but we also want to be consistent with the actual data source that we want, right? Caching is basically making a trade-off between being as much as it is possible up to date and waiting for the response from the data source, right? So what you want to think about when thinking about caching is how are we going to handle stale data and how are we going to invalidate the data in the cache? What are the strategies that we want to use to come up with what is invalid? What is the strategy to keep the consistency between the cache and the source of the truth? There are actually two different patterns to deal with writing to the data source, the write through and write behind patterns, and then the database synchronization and listening to the changes in the database or in the data source. Okay, let's talk about cache invalidation patterns. So there is a couple of them actually. One is based on time to live settings. So basically, when you set up your cache, you can tell, I want entries to be evicted after some amount of time. So I want them to be invalidated when this much of time has passed. So that's the most simple and the easiest one to implement. But then you can also listen to data changes. If you have some way of listening to those changes, you can invalidate on update. So you can catch the actual event and then update the data in the cache in response to this event. About writing to the cache, so you can actually do things in two different ways. You can update the cache and database synchronously in like one single transaction, for example, which I would not recommend because usually that means that you're going to have lock contention and other kinds of problems in this vein. And you can also have a write behind strategy. Basically, you update the cache first so that other clients of this same cache can have the most recent data and then persist those changes asynchronously. There is a problem with that approach as well because you might actually end up with data written to the cache but not to the permanent store if there is a failure of the permanent store during the update. So again, that's a trade-off. You need to choose which one works for you better. Okay. Let's talk about resilience. Basically handling failures and degradation. If you have a distributed multi-node cache, some of those nodes might and will go down, and you need to be able to deal with that. So you can have this cache aside pattern, basically keeping the data not only in the distributed cache but also in the local cache. You want to be able to implement a circuit breaker for failed cache operations. You need to be able to fall back to the original data source when cache isn't available, because I've seen it actually to happen some time ago that the application couldn't work because the cache didn't work, and that's a very bad pattern, right? You don't want this pattern to be implemented in your code. Okay, and then replication. Backup might not be that important, but replication and distributing the changes in the cache, that's one thing that you want to look at it as well. Okay. So implemented resilience. One thing that you want to check your cache against is whether it handles graceful degradation and whether your application remains functional without cache. More requirements. I've mentioned that before, but it's still worth looking at. When picking your caching solution, you want to monitor things like its health and effectiveness. Basically, that means that you want to know how often do you hit the cache, how often you are able to pull the data from the cache and not from the data source. What is the eviction count? How many entries in the cache are evicted or made invalid, marked as invalid? And what are the reasons for the eviction? In case of Java, there is one thing that you want to pay attention as well, that's memory usage, and especially in case of in-process Java caches, that the garbage collector pressure. So the thing here is that when you have a cache implemented in Java, by default it will store objects on the heap, right? And once those objects are evicted from the cache, they are garbage, they need to be collected. If there is a huge turnaround in those objects, then you're going to create pressure on garbage collector, and that will affect the performance of your application, because it will mean that more CPU cycles will be spent on garbage collecting and less on the application itself. Okay, and then the other metric that, or thing to observe, to implement in observability, is performance metrics. Basically latency, how much time does it take to actually pull something from the cache, and throughput. Okay, so again, caffeine, provides stats API. There are built-in metrics that you can use. Redis has this Redis info. And Micrometer, that's a solution from Spring. You can use Spring, and probably who is using something else than Spring to build their Java applications? Drop Wizard? Quarkus, okay. So Spring has Micrometer. Quarkus, I believe there is also some solution pretty much the same. So again, you want to be able to be sure that your caching solution supports Micrometer when implemented caching solution in your Java application. Okay, and then concurrency. In the case of caches, reading is not a big deal, right? So when you read from a cache, there is no problem with concurrency. It's the writing to the cache that makes a problem. Especially under high concurrency, you want the operations to be thread safe. So you want your logs, for example, to be very fine-grained. You want to be able to do things like compare and swap and do atomic operations. And the most important thing, I think, in case of concurrency is preventing cache stampede. What is cache stampede? So a cache stampede happens when in a concurrent application an entry in the cache expires, and then you immediately have lots of requests from different threads for the same entry. And then all those requests cause the reloading of the cache entry. So this means that instead of having one reload operation or update operation for your caching entry, you have as much as you have threads asking for the specific entry from the cache. So one way of avoiding that is refreshing before expiration, and that's what Caffeine implements with loading cache. So you define a cache loader. Basically, that's a piece of code that tells the Caffeine cache how to refresh a data with specific key, right? So you can set up your Caffeine cache so that the time to live is, for example, 15 minutes, and the reload is 7 minutes. So it means that when 7 minutes pass, Caffeine will do the reloading in the background. So you do not need to request it from Caffeine. It will do it on its own. It will schedule reloading of a particular key that is about to expire, and then when the time to live passes, it already has the fresh data, right? So that's one solution, but it requires an additional database load, right? Okay, the other strategy to prevent cache stampede is request coalescing. So basically that means that the cache itself it recognizes the situation that, okay, so we've got lots of different threads asking for the same data. So we wait a bit of time before we actually do the reloading for the specific entry. One way of implementing is that we return the old stale data, and then in the background we schedule reload, and then for the next queries to the cache we will return the new data. And then the other strategy that might be implemented as well, so that's random expiration. So when you set time to live for your entries in the cache, it's just a guideline for the cache. So it's going to actually pick some different amount of time to evict a particular entry and distribute the loads to the cache in time window. But that makes the cache behavior much less predictable. Okay, and then one other option, very popular, is cache swarming. So you basically load the cache when your application starts. The thing is that you need to know what are the popular keys that are going to be used by this cache. So you need to know that in advance. Okay, so let's move on. One pattern that I would like to cover as well is multi-layer caching. That's a very popular approach. So you combine level 1 cache, which is in-process cache, like for example caffeine, that provides you with immediate responses, with level 2 cache, for example implemented with Redis. So you've got, like in the CPU, you've got level 1 cache for the most recent data, most recent instructions for the CPU, or the nearest instructions for the CPU. Then you have the level 2 cache for things that are also quite near the CPU, but still can be loaded later, and so on and so forth. And it's very popular to also implement the caching on the edge, right? So when you have some kind of a web page in your web application, and it is already rendered, you can cache it as well, right? So this is one thing that you want to keep in mind as well, that it might be just enough to cache the actual rendered web page. Okay. There's one specific requirement that you might have when you're using database. So you want to cache the results of a query to a specific database, especially when you're using Hibernate or other object relational mapping. So it's good to check if your caching solution supports ORMs out of the box, and maybe it can provide you with things like cache warming for some predictable queries, right? For example, when you have like some kind of a table that you display in your initial view of the application, why not put it into the cache already when your application starts, right? Or when the user session starts. Okay. And the last thing that I want to talk about is cache's efficiency. Well, basically, a cache needs to be kept on a leash so that it doesn't grow too big. So you want to pay attention to optimizing storage and resource consumption of your cache, basically memory. Some caches provide you with data compression and serialization optimization, especially if it's a distributed cache. In case of JVM in-process caches like caffeine, you might want to look into something like off-heap storage. Who knows what is off-heap storage? Okay, so as I mentioned before, usually you keep your objects on a heap in Java Virtual Machine, right? But as I mentioned before, this is subject to garbage collection. So you might want to keep things in the memory, but outside of the heap, and manage the memory for it manually. And that's basically it. There are APIs in Java Virtual Machine, and there are cache implementations that use this possibility to store the data outside of the heap, outside of the garbage collector, and manage the memory themselves. Okay. And then the last thing that you want to do when you're implementing your caching solution is to look at the costs, if the cache is actually making difference, because you might end up implementing a huge caching solution and then it doesn't improve anything. So why bother? Okay. So that would be the summary. Like, if you want some guidelines from this presentation, that would be the guidelines. If you have a specific particular need that is very important for you, look at this slide. And then one thing, cache anti-patterns to avoid. So what are the troubles that you get into when using caching? Cache stampede, already mentioned. Stale data. So when you don't have a good invalidation strategy, you can end up with data that is just outdated too much. You can end up with cache bloat, so you need to be remember about giving the cache some bounds. And then silent failures, which is something that I've seen happen, as I mentioned before, you need to make sure that your application works without cache anyway. And that's pretty much it. Thank you very much. Do you have any questions? Now would be the time.
So you've mainly talked about caches in general, but you didn't really say when it would be beneficial to use the caches over the standard database requests or other like I/O operations, right? So could you give an example of where you wouldn't implement a cache, where it would be a terrible idea to actually have a cache, and where it would be a good idea to have a cache?
So it's very easy to come up with an example when it's a good idea. Like, for example, you have a query that basically takes too much time on the database. Like, say you have a view on your application, the requirement is that it needs to render in 2 seconds, 5 seconds, and the query to the database takes 17 seconds, right? So basically it won't work that way. So you need to have caching enabled for this kind of situation. When it would be a terrible idea, when caching doesn't improve things, so you need to measure. That's basically it. Basically, it boils down to user experience, in my opinion, at least, right? So if the user doesn't perceive the application is slow, you don't need caching. If they see that the application is slow, then you need to think about improving. It might not be caching that it will improve. For example, you might need to optimize your query first. But I would say caching is the last resort, and usually it brings a lot of trouble to the table, and then you need to solve the problems caused by caching as well. So it's not something that I would employ as a first line of defense, right, in case of slowness in your application. Yeah.
Okay, so I have a question about cache propagation. So let's imagine the situation when a new instance joined the cluster and it doesn't have all the information from in cache. Is there any protocol or standard or maybe way to actually synchronize caches, especially local ones, between all the nodes in the cluster?
None that I am aware of, but I might not know everything about it. But I've actually seen it implemented manually. So yeah, usually when you run in cloud, for example, I've seen it at Atlassian where we were using AWS. So we had built the two-layer cache, and we used simple notification service for that to actually inform about the changes in the cache. And it was not loading the cache, but informing about, okay, so there is a new instance, so it needs to grab some data, you need to send the data to it, or there is a change in a specific key for the cache, so grab the data from this particular node. That's how I've seen it implemented. Did that answer your question? Yeah. Okay. Anyone else?
Maybe another one for me.
Sorry, there's one guy more. We'll get back to you.
Yeah, I just wonder, because you mentioned memcached, right, as a quite well-performing solution, but also it is using the string pairs of keys and values, right? So I can imagine that with some data structures, it might be giving quite a lot of overhead to basically serialize it to JSON, for example, right? So did you have some experiences, or maybe can you imagine a situation that you will basically change the solution of caching because of the data structure? So for example, for simple data structures, you will use a different tool, then for more complicated, a different one, or the overhead is negligible?
A very nice question. Thank you very much. I haven't seen in the wild a solution that would use two different caches because just of different differences in performance. It's just too expensive, especially if you're in the cloud, right? So no, I don't think so. You need to wait and choose the solution that will be the less worst of the solutions, basically, in that kind of situation. Okay, one more question.
Okay, so yeah, in our application, we used to have a lot of caching, but we decided to actually remove part of it because it turned out it was additional layer. It didn't add any value. Do you have any like framework or strategy to actually be able to answer this question? Where to add this caching and when? I think when is also quite crucial here.
Well, it all boils down to observability. I would say you need to have the data, and it would be best if you could run the same scenario simultaneously to see what is the response time when you're using cache and when you're not using cache. You could use some kind of like feature flags implementation for that, but that's a very broad topic, so I don't want to get started on it because that would be another presentation. Thank you for the idea. But then there are solutions or patterns for doing change data capture that would help in that case as well. Sometimes it's just enough to think about if the data source that you're using, the database, is the proper tool, right? But maybe you could use MongoDB instead of Postgres and you would be good with that. And you would not need caching at all. As I said before, caching is the last resort. That's something that is extremely painful to tune properly, and it brings its own problems to the table when you start implementing it. You need to deal with statelessness of your data. You need to be aware of the eventual consistency that it brings. It might be too complicated in many cases, and sometimes it's just changing the database type that helps a lot.